Hey everyone, this is Sam Shark with the Clown Shark Batwing team, and we're here today to answer the question, what in the absolute hell is a sigma? This is something that I think is really not explained very clearly in most places, but it's really something that's actually quite simple. So we're going to go through this visually today and clear out most of your questions about it. And it's a very useful thing to have a mastery of. So we're going to use flux for this, and one of the big reasons is simply because the way the sigma schedule is set up is from 0 to 1, so it simplifies the math a little bit. You can see I've got some of these preview nodes set up here for you to look at. Highly recommend using these regularly until you're more comfortable with what's really going on. It can really help you understand how the sampling process really works. So anyway, got another interesting feature here that I have not introduced yet. Uh, there's this node called extra options, and we'll just use a couple of these things, but what we can do is type something into this node, hook it up here, and we're chaining all of these options down the line here, each of these nodes displaying one step, 8 total steps. And it will allow us to change what's shown in the preview. So typically in the preview, what you see is the denoised prediction at each step. You will see the best guess of what the image would look like if the model had to say, all right, screw it, we're done. We got to just cut it off right here, and we're just going to shit out what we got now. No questions asked. And that's just where we stop. Um, so that's useful because it allows you to see really what's happening with the image. But we've all seen some of these nodes where you see something that looks really noisy for a while. It's just like pure white noise, and then gradually you see what maybe looks like a little bit of a shape. Well, that's what the latent image actually looks like. It's actually very noisy throughout the most of the process. What it's doing with each sampling step is it's removing noise until you're done. So enough talk, let's see what this actually looks like. So on the top here, we've got one that's more curved. On the bottom, we have one that stays very high and then drops off very suddenly toward the end. So since we're doing only 8 steps here, I'm using a relatively high order sampler, Res3S. This one's accurate enough that you can actually get away with 10 steps, stuff like that, and actually get a coherent image out of it. All right, so we got the first one, and really not all that bad for only doing 8 steps in such a dramatic sigma schedule here. And up here we have one that's a little bit more balanced. So what I'd like you to look at now is what looks so different between the previews here. So on the bottom, this is just like pure noise for the first 1, 2, 3, 4 steps, and almost entirely noise for step 5. Now let's go look at the sigma schedule. 1, 2, 3, 4, 5 that are very, very high up here, and then it starts to drop, but still really noisy. That's this one here, and then very suddenly 1, 2, 3 steps, 1, 2, 3, all the noise is gone, and we're done. This one here is much more even in its approach, and I think that's pretty clearly reflected in the previews here. You can see the noise is being removed at something much more approximating something linear. So there's advantages and disadvantages to both of these approaches. Traditionally, what we used to use was something like SDXL or Stable Diffusion 1.5 or Stable Cascade, was something that looked much more like this here, where it dropped off very suddenly and the model had to spend almost all of its steps refining that last little bit of noise, which is going to correspond to the details. So when it is at the very top here, removing very tiny amounts of noise in the beginning, what it's doing is setting the composition, um, the overall structure of the image. And here it's spread out a lot more evenly than it is here. So with models like Flux, HiDream, uh, WAN, the video model, all of these, they usually benefit from spending most of their steps in the high part of the Sigma schedule and then dropping off really suddenly. So it's kind of like a ready, aim, fire approach. Once the trajectory is set, the rectified flow, they're supposed to go in a straight line. Once the trajectory is relatively set, you can just kind of let it go and take out most of the rest of the noise. Um, that's not without a price, though. If you are doing all of this all at once, you do lose some quality in the details. That's where the beta and the beta 57 schedulers come from. They spend most of their time on the higher part of the Sigma schedule, but then there's a little bit of curvature toward the end to get just a tiny bit of that effect we used to have for refining those details. Um, so when you're looking at something like SDXL, if you look at the preview here, you'll see at the top, it will say something like 14.6 instead of 1.0. You can just rescale it. Whatever the number is here, divided by whatever that top one is, that's the percent of noise that's left. So like right here at this sigma in the center of this, corresponding to step number 4, 60% of the noise is left. 40% has been removed. If you go all the way down to step 6 here, you've got about 75% of the noise left, and there's about 25% left. And that looks about right for what we're seeing here. Issue that happens sometimes with schedules like this is that if you look at the numbers here, that's 0.4. You are removing 40% of the noise in one step, which is quite a lot to ask sometimes. So it turned out relatively okay here this time, but if you really start to zoom in, you can start to see some of the issues. It held up relatively well, but yeah, that's a lot to ask. Mm. Okay, so what is a step size and how does that relate to the sigma? Well, one, step size, this is something you sometimes see buried in math papers with crazy symbols that you don't need to understand 99% of. Delta T, that's just our step size, and our sigma level ultimately. I've got this extra little node here called Sigma's schedule preview. And what it does is it will actually graph some of these things. So right here, this is sigma, and this is this cyan colored line here. That is what the next step looks like. So you can see, like, as it's changing here, this gap is getting bigger. Delta T, that's the step size. So you can see, same thing, 40% of noise being pulled out in that last step. Don't need to use it, but can be useful to help shed some insight on it. Okay, so aside from that, one caveat that I think is worth pointing out here is that these are always changing here. The change might be small, but there is some change. If you repeat a sigma, if you have the same one 2 times in a row, you have a step size of 0. And that doesn't make a lot of sense to the model, or to the sampler. So you can often end up with problems with that. You might end up with a black image or something like that. Okay, so one other thing that I think is worth showing at this point, with regard to the sigmas, is what the hell is actually going on with shift. So let's try setting this to like 100 here, something really extreme. You can see this starts to look a lot more like the linear quadratic one. So what we're doing is shifting everything upward and causing more of the steps to be done on the composition setting steps, sigma levels, and really just saving all of the details for one step at the end here. So how is that going to turn out? Well, we actually do have 4 fingers and a thumb there, which is something consistent with it spending a lot of time thinking about the composition, but there's some really bad problems with the detail there. Looks really grainy and kind of nasty. Now, if you go the other direction here, say drop this down to 1, now it's a lot flatter. This is almost linear. And we're gonna let this one run, and we can see noise is already coming out in this first step here pretty early. We got a really silly looking beast forming here. No shark head. Now, why no shark head? Well, maybe it's because it didn't have enough time to actually work on the composition. But the details look much better. That really nasty grainy look is gone and is replaced with a really sexy leg. Okay, so that's what the shift does. And again, I suggest having Sigma's preview up so you can see it. With regard to how this is hooked up, by the way, with the Clown Shark sampler, um, you can think of the scheduler here as basically the equivalent of hooking up the basic scheduler here. This will override it. It's going to completely ignore whatever's punched in here if you have something hooked up externally. So this is like your custom Sigma's input, just like you would have for Sampler Custom Advanced, where you'd hook that up, does the exact same thing. Okay, so what about the topic of actually removing noise? What the hell does that really look like? So let's go with a relatively straightforward example here. So what we're going to do now is get rid of this, throw this off to the side, cast it away like we are doing with everything of value in our civilization today. And we're going to hook up a prompt, red, fire, something with a color component, so we can actually see what's going on here. And see at the bottom here, it says X preview. So we're going to be looking in the bottom at what the latent looks like. EPS preview, this causes it to show what the model predicted the noise to look like, as in the model says, hey, subtract this noise from the image and you will get the denoised image. So let's just run this and see what it looks like. All right, so we are getting fire. Should probably be the primary source of energy production within 5 years. And holy crap, it's the opposite color there. And if you think about it, that actually makes a lot of sense. So if you have something that doesn't really have any color bias, noise by definition, it's kind of a brownish neutral tone. Well, think of it this way. If you wanted to turn something that is white red, you would add red to it, right? Well, if you subtract red, you might get blue or vice versa. So what we're doing here is this is the prediction the model's making, and we are subtracting it from what we see in the bottom, and the amount of it that we subtract is multiplied by the difference between these two sigmas. That's your step size. So maybe your step size is 0.1. You remove 0.1 equivalents of this, and then maybe down here, if you had a really big sigma, you might be removing 0.4 times this here. But ultimately, that's all it is. It's just straightforward, simple arithmetic.